Hi, everybody. Thanks for having me here on this panel and giving me a chance to talk to you today. So, I'm going to talk to you a little bit about the quantum engineering program that we've founded and of which I'm director at Colorado School of Mines. Just very briefly, talking about what we're trying to achieve with a quantum engineering program and what we think that means, talking about the challenges of and opportunities of instructing undergraduates in quantum engineering and our approach here at Mines. And I should say that a lot of what I'm going to say today expressed much more at length and probably much more eloquently in this position paper that I think a number of people in this room are actually part of, called Building a Quantum Engineering Undergraduate Program. It's on archive there. It's appearing in IEE Transactions and Education very soon. I encourage you to all go look at it. Just to open, what is quantum engineering? If I had to put a label to it, I would say it's the project of leveraging the exotic properties of quantum mechanics for practical, scientific, commercial, and national security gains. And why I start with this is I want to say this is a hugely interdisciplinary endeavor. So if you think, for example, of what it will take to build a fault-tolerant quantum computer out of superconductors, if you look at all the different tasks on this list, and which I've kind of tagged by what department they come from, you see just for this one project, there's a half dozen different disciplines that participate in it. And the core challenges of quantum engineering are no longer mainly physics by any stretch. I've even seen slides presented by, I think it was Google, where they presented their approach as physics de-risked, right? Taking sort of the challenges of physics out of the equation. And to do this, we need to get these kind of mega projects to work, we need a quantum literate workforce that's drawn from a wide array of disciplines. And in other words, engineers that can use the unique skills of their discipline in a quantum context. And that means that the natural home is not really in one department, particularly because only the very wealthiest schools in the country, I think, could stand up an entirely new department in quantum engineering. And I don't even think such things are necessary. So what kind of programs do we need? So there's a few set of recommendations for how you would structure an undergraduate program in quantum engineering. We see these at Mines. We have a four plus one master's programs. Traditional thesis and non-thesis masters and undergrad minor. And the core principle we started with was assume no physics background whatsoever. And the reason for this is the rigidity of a typical four-year physics major structure can be a barrier. It's hard. There aren't all that many physics students. If students are taking physics simultaneously, quantum mechanics is not covered in first year physics anyway, not really till third or fourth year. And the traditional third or fourth year course is not terribly relevant to modern quantum information science. So if you require physics, you're asking a lot and severely restricting your applicant pool in a way that does very much hurt diversity without all that much benefit to what kind of quantum mechanics you can teach. And so the way we structure it is we offer a core Quantum for Everyone course that covers the basic foundations of both quantum mechanics and QIS. And importantly, this is not just a quantum computing class, as I'll get to in a second. And we require only a college level linear algebra course as a prerequisite, which means that this can be taken as early as sophomore year at Mines. I'm fortunate to be teaching this at a primarily STEM school where I think about half our majors require linear algebra. So we have a lot of students to draw from. But we think that linear algebra is not that big of an ask. We then follow it with a range of more advanced courses that are targeting key skills, which are not only quantum in terms of the electives that can contribute toward this degree. And in terms of a master's degree, we've found it beneficial to split into software and hardware tracks so students can better focus the education. If you only have 1 year, we thought it was beneficial if you wanted to focus on software or hardware. But anyway, as I said, it's an interdisciplinary program that joins physics with electrical engineering, computer science, applied math, materials engineering. And I'm going to focus on the undergrad minor today, but most of the comments apply to what students could take at a master's level at higher depth and with longer assignments. So our new core courses that we launched to launch this program, which are all joint undergrad grad classes at Mines, because anything you offer as 500 level at our university will be half undergrads anyway. Is the Fundamentals of Quantum Information class, which is Quantum for Everyone. It was taught by me, only linear algebra prerequisite. Low temperature microwave measurement, which is launching this spring and teaches students how to take, load, configure, do experiments, and take data in a helium refrigerator. This was a skill set that was when I surveyed employers in helping craft this program, that was one of the skills that was asked for repeatedly. Quantum many-body physics, which is a more advanced physics class, and about many-body quantum mechanics, and quantum programming that I'll get to in a bit. And I should say that all of this is supplemented by a developing program in optics. We have a very strong laser physics group at Mines, which is relevant, obviously relevant to AMO and photonic quantum information science. And then to finish out your minor or master's degree, you can take from a list of a wide range of quantum and non-quantum electives drawn from our participating departments. Because, as I said early on, the problem of quantum engineering is very interdisciplinary, and there are tons of skills like microwave engineering, machine learning, data science, materials characterization that are not strictly quantum but are really valuable to actually helping make these things work. So the Quantum for Everyone class, the way that we teach it follows a modular structure that as follows. We start with a week on linear algebra because the students need that refresher. I think we're actually going to move that into the summer beforehand to really give them more time to get solid on linear algebra. That was what they requested. Properties of a single qubit. Note that you do not want to cover continuous variables. You introduce a ton of multivariable calculus. As soon as you do that, anyone who is not coming from physics at math is promptly lost. And then 2 or more qubits, entanglement and gates, Hamiltonians and time evolution, perturbation theory, which is definitely a controversial thing, time-varying Hamiltonians, gate model of quantum computing, and canonical algorithms and speed-up mechanisms, which is really like showing like this is why, going over things like Shor and Grover and phase estimation to say this is why people wanted to build a quantum computer in the first place. Observations from teaching it last fall. Half non-physics students, and I was very pleased that at the end of the day there was very little correlation between major out of 30 students that finished the class between major and class performance at end of course. Avoiding continuous variables made many body problems tractable. Perturbation theory is hard, but again, when your only tool is a hammer, every problem is a nail, and this is your only tool besides high-level numerics or actually using a quantum computer. The big one thing I wanted to highlight is that the biggest points of confusion were translation issues. So finding different ways to express the same thing, something can be very natural in one language and hopeless in others, was really hard for students, I think, and that's a work in progress. And I want to highlight that simulation problems where you just do small scale numerics, like, just integrate time evolution for 2 spins or something like that, is really valuable as a useful tool because it's accessible. Any student with Mathematica can do it. And it's really valuable. So moving on, I also wanted to highlight, experimental techniques. As you all know, it's very specialized and very expensive equipment in QIS, and how to make this accessible at a classroom level, not just, well-funded faculty research labs, is a key problem that is very much something that I think we need to address as a discipline moving forward if we want to teach a lot of quantum engineers. At Mines, as I mentioned, we offer low temperature microwave measurement, a micro that I already discussed, microelectronics processing, where students learn to fabricate and test devices and do lithography and things like that, and laser physics courses for, to teach students how to align optical tables, do spectroscopy, calibrate and characterize lasers, and so on. And we think that this covers a good chunk of what students will need entering a quantum technology lab. And then finally, I wanted to highlight our quantum programming class. Smart NISQ programming is a real art form. Getting a NISQ calculation that's of any size to go well is hard. This is not a common skill set. This is something that a lot of non-quantum employers repeatedly ask for, was like, can you teach someone to actually program a quantum computer? Can you get something useful out of it? And I want to highlight NISQ. I personally am kind of a NISQ maximalist. I think that are going to be commercially viable applications of NISQ that will remain viable even after we have error correction. We won't fully understand the potential of it until a lot of people try their hands at it and the hardware further improves. And if we focus on the fragile algorithms where a single error gives you a garbage result, you're really telling students, hope you remember this in 2030. Right? I mean, and that's not a good motivator. So at Mines, this is taught through our quantum programming class, which focused on variational algorithms, simulation, and the principles of error correction. We instructed students in a variety of error mitigation techniques. And I want to highlight that access to real quantum hardware for this class is critical. I'm out of time, so I'll just finish. But I say last spring we were fortunate enough to be granted access through Google to their Sycamore processor, and so students got to submit jobs there, which was a really exciting experience. But I'm out of time, so I'll just say thank you all, and happy to take questions during the panel.